Example 3. Find the value of the solid obtained by rotating the region bounded by y equal to x cubed, y equal to 8, and x equal to 0 about the y-axis. So this is y equal to 8, this is x equal to 0, and this is the curve for y equal to x cubed. Now that's the region bounded by this three curve. You're going to rotate this region about this y-axis. So this symbol indicating it's rotating about this y-axis. So we got a solid like this. To find the value for this solid, we slice them horizontally this way. Okay. So each one is kind of like a disc. For one particular disc, that will be the base area here times the thickness. The thickness over here is delta y, so that will be dy. And the base area over here, the cross-sectional area over here will be pi times r squared. But this r here corresponding to the x coordinate of this point. So if you label this point x comma y, then the r here corresponding to the x coordinate of this point. So the cross-sectional area here will be pi times x squared. Pi times x squared. Now, because this is the integral with respect to y, you want to express this x in terms of y. So we have y equal to x cubed. So x will be equal to q root of y. So you will have this x to be q root of y. And when you square that, so when you square this, then what happened here is this 3 will be in the denominator here in this exponent, that corresponding to the index or the root. The 2 here will be on top in this numerator in this exponent. Okay. So that's equal to this integral of pi times y to the 2/3 power. When you find antiderivative, exponent is going to go up by 1 and then times the reciprocal of this exponent. Now, substituting 8 into y, substituting 0 into y, do the calculation, that is 96 pi over 5. So the value for this, solid here, it is 96 pi over 5. So that was example 3. Example 4. The region, let's call that R, enclosed by the curve y equal to x and y equal to x squared, is rotated about the x-axis. Find the value of the resulting solid. So here is the graph right here. So this is y equal to x, this is y equal to x squared, okay? When you rotate this region about this x-axis, you get a solid like this. Notice the solid here is kind of
hollow inside.
It's kind of empty inside, okay? It's kind of like a loudspeaker, you know, like a loudspeaker like that. So the cross section is like a washer, okay? Now for washer, the value for that is going to be the cross-sectional area times the thickness. In this case, the thickness over here is delta x. The cross-sectional area is pi times the big R square, subtract pi times the small r square. So you can take out this common factor pi, so big R square subtract small r square times the thickness. Now in this case, what will be this big R, the outer radius? Well, that will correspond to this y coordinate of this point, right? From here to here, that's the y coordinate of this point on this y equal to x. So y coordinate on top over here is equal to x. So it's the same as this x over here, whatever x coordinate here, okay? What about this small r? What about this inner radius r? That corresponds to y coordinate of this point on this curve y equal to x squared. So y equal to x squared, so y equal to x squared here. So the small r corresponds to r squared. Okay. Now you substitute this x into r, x squared into small r. You got this integral. Okay. So substitute this x into big R, x squared into small r, and replace delta x by dx, and x go from 0, and it's going to end it at where? It's the last one here. X is going to end it at 1. So this integral will start from the lower limit will be 0, upper limit will be 1. Okay. Simplify this integral. You got this. Now you find this integral. You can take out this pi in front of the integral because that's a constant multiple. Find antiderivative over here. That's x cubed over 3. That's x to the 5th over 5. Evaluate here, x go from 0 to 1. Do the calculation. So that will be equal to 2 pi over 15. So that's the value for this solid over here. Okay. In the above examples, the method that we use to find the value is called the disk washer method. Sometimes the cross section is a disk, sometimes the cross section is a washer. Okay. So it's not your dishwasher method, okay? It's a disk washer method. Remember, if the 2 points are on the y-axis, to find the distance, you use a y-coordinate on top, subtract the y-coordinate at the bottom. So it is y2 minus y1. Example 5, we try to find the value of the solid obtained by rotating the region. Okay, in example 4, the one we just went through, okay, about the 9y to the 2. So this is the region in example 4. So y equal to x over here, y equal to x squared over here. Then that's the region bounded by y equal to x and y equal to x squared. Now this time we're going to rotate about this y equal to this horizontal line over here. Okay. Now we're going to get a solid like this. Okay. Now to find a value for this solid, we're going to slice them vertically perpendicular to this horizontal line right here. So each one here is like a washer. Okay. Now let's think about what will be the outer radius and the inner radius. Now when you think about outer radius and inner radius, always go from the center and then look at this original region. It's not up here. Original region is this highlighted region here. This is the region that we have. Okay. So from the center over here to this, the outside over here. Okay. So that's a big R. Okay. Now this line over here is y equal to 2. This curve over here is y equal to x squared. Okay. So the big R will be this y on top, subtract this y down here. So that will be equal to 2 minus x squared. So that's the outer radius. What about this inner radius, small r? It's from here all the way to this inside. So for this one here, this is y equal to 2. That's the center. And this one over here is on this line y equal to x. Y equal to x. So this small r corresponding to this y on top, subtract this y down here. So that will be 2 minus x. So there will be 2 minus x here. Now the cross-sectional area will be pi times big R squared, subtract pi times small r squared. So this will be, this is a big R and that's a small r. So the value for this solid here is going to be the integral of this. And the thickness, remember the thickness of this washer here is going to be delta x. Okay, that's the thickness of the washer. So that will be dx over here. Now ax is this one over here. So we just put it down. to find this integral, we expand this using the perfect square formula, and this one using the perfect square formula. Combine nitrogen, we got this. And you find anti-duality, and x here go from 0 to 1. So the result here will be 8 pi over 15. Now the solid in example 1, 2, 3, 4, 5, those are called solids of revolution because they are obtained by revolving a region about a line. So they're called solid of revolution. Okay, so let's summarize and review what we, the disk washer method to find the value for solid. So basically the value will be the integral of the cross-section area. If the solid is oriented this way, then the value will be the integral of this cross-section area. The thickness of each disk right here is going to be dx. X over here go from A to B. If the solid is like this, then the thickness of each disk here is going to be delta y. So that will be dy. And y go from C to D. And this cross-sectional area will be A, but it's going to change as the y change. So we call it AY. Now, this cross-sectional area, if it's a disk, that will be pi r squared. If the cross-section is a washer over here, area will be equal to pi big R squared, subtract small r squared. Big R is the outer radius, small r is the inner radius. So let's take a break.